In mathematics, a universal statement claims something is true for all possible cases. Now, to prove it false, we only need to find one single case where it fails. This is called a counterexample. Now, consider this statement. For any real number x, if x squared is bigger than 9, then x is bigger than 3. This seems direct at first. If we think of numbers like x equal 4 or x equal 5, it holds true. Now 4 squared is 16, which is greater than 9, and 4 is greater than 3. But the statement says for any real number x. This includes negative numbers. So let's test a negative number like x equal to minus 4. Now check the condition. Is x squared bigger than 9? Minus 4 to the power of 2 is equal to 16. 16 is bigger than 9. The condition is true. Now let's check if x is bigger than 3. Minus 4 is bigger than 3. This is false. So it is not met. We have found a value x equal to minus 4 for which the if part is true but the then part is false. Therefore, x equal minus 4 is a counterexample. The original statement is false. Now remember, finding one valid counterexample is all you need to disprove a for all statement. In our second example, we're going to prove that the square root of 3 is an irrational number using a powerful technique called proof by contradiction. First, we assume the opposite of what we want to prove. Let's assume that radical 3 is a rational number. By definition, this means we can write it as a fraction. So radical 3 in that case will be equal to p over q, where p and q are integers, q is different than 0, and the fraction is in its simplest form, meaning p and q have no common factors. This is the key assumption. Now, let's work with this equation. Squaring both sides, we get square root of 3 squared is equal p over q all squared. This implies that p squared over q squared is equal to 3. Let's rearrange it. 3q squared is equal to p squared. Now this tells us that p squared is a multiple of 3. Now, a key number theory property states that if a square of an integer p squared is a multiple of 3, the integer itself must also be a multiple of 3. So we can write p as 3k for some integer k. Replace p in the original equation, we get that 3q squared is equal to 3k all squared. Let's simplify it to get 3q squared is equal to 9k squared. Divide both sides by 3, we will get q squared is equal to 3k squared. This tells us that q squared is a multiple of 3, which means that q is a multiple of 3 as well. We have deduced that p is a multiple of 3, q is a multiple of 3. This means that p and q, they share a common factor of 3. This is a direct contradiction to our original assumption in step 1 that the fraction p over q is in simplest form. When you reach a contradiction, your starting assumption must be wrong. Therefore, our assumption that radical 3 is rational is false. We conclude that radical 3 is irrational. In our third example, we want to show that the equation 2x squared minus 4x plus 1 equal to 0 has no integer solutions. We'll prove this by contradiction. Let's assume that there is an integer solution. Let's call this integer solution k. If k is a solution, it must satisfy the equation. So 2k squared minus 4k plus 1 must be equal to 0. Now let's rearrange this equation to isolate the constant and factor the remaining terms. Moving the k terms to the other side, we get 1 is equal to 4k minus 2k squared. Now take 2 as a common factor on the right side. You will get 1 is equal to 2 times 2k minus k squared. Now if you look at the right side, it's of the form 2 times an integer since k is an integer. This means that 1, which is an odd number, is equal to the right side, which is an even number. This is a clear contradiction to the fact that 1 is always odd. Because our initial assumption led us to this impossible conclusion, the assumption itself must be wrong. Therefore, there are no integer solutions for the equation 2x squared minus 4x plus 1 equal to 0. Now remember, this is extremely important in IB. Such a question came in the externals more than once, and this technique will always work when you use it in the correct way. Now we will use proof by contradiction to prove that there is no largest even integer. Now, as usual, let's assume the opposite. Let's suppose that there is a largest even integer. Let's call it n. Now, since n is an even integer, by definition, it can be written as 2k for some integer k. Let's create a new integer m by adding 2 to n. So, we will have m is equal to n plus 2. Now, m in that case will become 2k plus 2, which is 2 into k plus 1. Now, since k is an integer, k plus 1 is also an integer. Now, this means that m, which is 2 times an integer, is by definition an even number. Since m is equal to n plus 2, it is clear that m is bigger than n. Now, we have successfully constructed a number m that satisfies two conditions. M is even and m is bigger than n. This directly contradicts our initial assumption that n was the largest even integer. Now, since the assumption leads to a logical impossibility, the assumption must be false. Therefore, we conclude that there is no largest even integer. Thank you for watching. We'll see you next time.